Hello, this is Mr. Huber. In this lesson, we're going to look at scatter plots and how we can model the data using linear equations. A scatter plot's just a representation of some data, usually x and y values, or again, inputs and outputs. And we see a couple examples of some scatter plots here. Again, points kind of scattered about the grid. So in this first example, we see that for the most part, there's a line that the points follow. Okay. In the second example, also a line that the points generally follow. In the third example, the points are really scattered all over the place. There's no real trend that they follow. So in that first example, that's something we call a positive correlation. Okay, a positive correlation, because this line we have right here is basically a positive slope. Right, a positive correlation. As the data moves to the right, it goes up. In this second example, this line would have a negative slope. That's why we say that has a negative correlation. Okay, again, if y increases as x increases. So as the x goes up, the y goes up. Negative correlation, the y goes down as the x values increase. And then over here, basically no correlation at all. So how are they related? These are related in a positive way, in a negative way, and not really much related at all. Right? The correlation can be referred to as a correlation coefficient, depending on how strong or weak the points are related to the line. So the closer all the points fall to the line, the higher the correlation coefficient. And it only goes from -1 to 1. So we'll see here. A correlation coefficient of -1 means the lines lie really close to the line. The points are really close to the line, but one with a negative slope. So this would be something that would have a pretty strong negative correlation. And the correlation coefficient would be pretty close to -1. Okay? 0, points don't really near lie any line. That would be an example here. That would be a correlation coefficient of around 0. And then when they're close to a positive slope, and the points here are all pretty close to that positive sloping line, that would be a correlation coefficient of close to a +1. Okay, so it's not the slope of the line, but it's how close the points are to the line that fits that data. Let's look at a couple examples here where we can try and describe the correlation in the data. So this first example would have a line that you could kind of draw in through here. Okay? They kind of follow that line, but they're not really close to the line. So that would be a relatively weak positive correlation. And the correlation coefficient would be positive, but it'd be relatively close to 0, more so than 1, because those points aren't really that close to the line. So it might be a correlation coefficient of 1/2 or a little bit less than that. In this next example, we're going to see that the points are very close to a negative line I could draw through there. Those points are all really close to that line, and that's a strong negative correlation. A strong negative correlation. Since it's strong, it would be closer to 1 and -1 because it's a negative sloping line. It's a negative correlation between the data. As the x values increase, the y values are decreasing. Okay, negative correlation, and this would be a correlation coefficient that's really close to really close to -1. Okay, because they're very close to the line, and it's a negative correlation. This third example would have relatively no correlation at all. So, relatively no correlation, and that would be a correlation coefficient of around 0. Right, when it doesn't really have much correlation at all, the points really are scattered. We can't necessarily say that as the x values increase, the y values increase or decrease, because as we go to the right on the graph, we got some points going up here, some down here. So there's really not a correlation we could show between those. So again, relatively weak positive correlation, because it is a positive correlation, but the points aren't really that close to the line. Okay, here, all these points are so close to the line, it's a strong correlation and a -1 because this is a negative sloping line. Right? Let's now, if we go back here, these lines are called a line of fit, the line that best fits the points. There's not a single line that goes through these points or would jump all over the place, even here, even though they're close. right? Those aren't all on a straight line, but we could fit a line that kind of goes through there. That's called a line. Look at what we can do to draw those lines that fit in the data. So those are called a line of fit. Okay, so the line of fit is that line that basically follows the data. We want that line to be really close to all the points. There should be just about as many points above and below the line. Okay, and we want to then be able to get an equation for that line that'll give us an idea of what's happening with the data. So we're going to see an example of how we can do that here below. This is data for the number of active woodpecker clusters in a national forest in Mississippi. Okay, so if we want to make a scatter plot, the first thing we want to do here, right, is make a scatter plot of the data. So I'm going to draw one down below here, and we don't have any negative values. None of these are going to be negative x's or y's, so we can just concentrate on this first quadrant. Okay, and if we do that, I'm going to move this up just a little bit so we can get that off the bottom of the screen a little and maybe see it a little easier. Right? This x value, 2004, is going to be the x value of 0. The year you start with will be your 0. Okay? And then we'll go from year 0 to 2014 would be 10 years after 2004. So we're going to have an x value of 10. So we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10. Again, we're counting by ones. Okay? And this would be years since 2004. 2004 is 0 years since 2004. 2005 would be 1 year since 2004, and so on. And then our y values go from about 22 there, we see. That's our low value, up to 51. So you may want to count by 5s or something like that. So we could count by 5s, 10s maybe. I'm going to go by 10s. 10, 20, 30, 40, 50. Okay? And now we'll be able to plot these points. So keep in mind, we're not going to put 2004 on our x-axis. When we're talking about years, you want to have a starting year, or a starting time sometimes if it's time, and then go from there. So we're going to graph these points now. So we have 0, 22. So 0, 22, maybe be right about there. We have 2005 would be x value of 1, 24. So right around there. Then we have 2006 is x value of 2 and 27. So right around there. Then we have, again, this is 3 because it's 3 years since 2004. And that's also 27, so it'll flatten out a little bit from that other point. And then 4, 34. So 4 and 34 right there, right between about 30, right, and 40. So right in that area. And then we're going to have 2011. We have to pay a little bit of attention. That's year 7. So you got to understand there that it's jumping a little bit. So we have 2007, or 2011 is year 7, and that would be, this would be 7 and 45. So that would be right around there. And then we have 2014 is year 10 and 51. So, right around there. So now we've got our data plotted. You can see it goes basically up as we go from left to right as we move to the right. So we would have a positive correlation in the data, and we're going to write an equation for a line that basically goes through the middle of that. So we're going to need to draw a line that basically follows that data, and that could probably be shifted down just a little bit. Let's try that again. Sometimes you might need to adjust as you draw this. A relatively straight line. That looks a little better. Again, a relatively straight line. We got a couple points above, a couple points below. And what we want to do now to be able to write the equation of that line is pick any 2 points on the line, okay, or at least that are the closest to it, and we can use those to write our equation. So I am going to pick this point right here because it looks like that kind of goes through there, and then we could use this one. Okay, those are 2 points that look like the line basically goes through them that we could use for our data. So that would be these 2 points right here, right? That's this point. And then your 7 right here, We could use those 2 points to write our equation. So when we write the equation, we're going to use those as our x and y values. So remember, this is 2, comma 27. So our 2 points are 2, comma 27 and 7, comma 45. And so we could write an equation using those points like we have any other time we've written equations before. We're going to need to find a slope. So we're going to do 45 minus 27 over 7 minus 2. All right? We do y2 minus y1 over x2 minus x1. Okay? And so we're going to have 45 minus 27 gives us 18 over 7 minus 2 is 5. We can just leave it as a fraction, 18 over 5. And then we could write the rest of the equation a couple ways. We could use point slope form, okay, or we could find the y-intercept and write it that way. So let's look here. What we can do is write 45 equals 18 over 5 times 7, okay, plus b. We want to solve for that b value. Okay, so we're going to have a little bit of difficult work here to do with some different fractions. That's fine. So we're going to have 45 equals 18 times 7 is 126 over 5. And we can maybe do 126 divided by 5, and we'd get 25.2. So this is plus b. So we'd have 45 equals 25.2 plus b. And then we could subtract the 25.2 on both sides, and we get 19.8 equals b. Okay, so now we have a b value, we have a slope, and so we could write the equation for that line as y equals 18 over 5x plus 19.8. That would be the equation for the line of fit that we have there, that blue line of fit. All right, takes a little bit of work. The numbers aren't necessarily easy. You know, we can use the fractions for slope, just keep it as a fraction. We can turn some into decimals if that makes some of the math a little easier there. And we've got an equation. We see a y-intercept of 19.8, and we could see that would come down a little bit lower than where the y-intercept goes for the actual points we plotted, but it's pretty close, right? Year 0 right here was 22, and we came with a y-intercept of 19.8. We got a line that, again, basically fits the data. It's not going to be perfect. And everybody's equation might come out a little different. They should be close, but depending on how you draw the line, which points you use, there's some variation that's going to fall in there. Right? Now we want to look at the last part of this. The reason we wrote that equation, why did we go to all that work? Well, now we can use that equation to say what would happen to some other points on the line that aren't there. Like what would happen in 1997? Okay, we didn't have any data for 1997. We could see what might have been happening then. We could also look at the year 2020. I'm going to just do 2020 as an example. That would be how many years since 2004. So the 2020 would be an x value, okay, of 16. That's 16 years since 2004. So we could plug 16 into our equation. So we'd have 18 over 5 times 16. And that is a fraction. If you're putting your calculator, it comes out to 57.6, then plus the 19.8. And so we'd have 77.4. So when we have an x value of 16, we'd have a y value of 77.4. Let's get that a little more clear there. Okay, so 77.4. So we'd expect 77.4 active clusters. We'd probably round that to 77 because you probably wouldn't have part of a group of birds. Okay, so we can use that line of fit to make predictions, to see what's going on with the data, to have a trend for what's happening with our plot of data. Okay. One nice thing that we're going to find here is that you're going to be able to use the calculator to get those lines of fit. I want you to understand what they are and where they come from, so when you're using the calculator, you have a better idea if you're on the right track or not. Okay, so we're going to be able to do some of both. Before we look at how to use the calculator to do this, let's take a penalty flag of trivia. There's only one American state flag that is not a rectangle. Most flags are rectangles. We see one there. That is actually the flag for one of the U.S. states, and it's not a rectangle. See if you can guess which one it might be. It is, of course, because they can't do much of anything, right, the state flag of Ohio. And if you could get my feelings for how they are there. So anyway, they, I guess, want to be different, not have a rectangular state flag, the only one. Good for them. All right. let's see how we can do this on our calculator. There is a separate sheet posted on the class page that if you pull up will give you step-by-step instructions for how to use your TI-83, 84, the different versions of that. There's some variations in there, so you might need to ask and say, okay, my screen looks a little different, or what's the right button, but they all should basically be the same, even though things might look a little different on the screen here and there. If you go through the instructions on that for this next problem, I want to make sure you know how to put that in, get a scatter plot of data, and get a line of fit, more importantly. Okay, drawing the points isn't that hard to do by hand, but getting that data for the line of fit, we saw that was a little bit tricky there in that last problem. So we're going to be able to have the calculator do a line of fit for us. Okay, and so what I want you to do is be able to take the handout there, look through the instructions, and plot these points that you see. Okay, I want you to plot what you see here in these x and y values. You're going to enter those. Again, the instruction sheet's going to show you how to put all these values into your calculator in some lists. So then it will graph the data for you, and then again, more importantly, come up with the line of fit. If you graph these, you're going to see that they go down from left to right. They have a relatively negative correlation. Okay, this data is relatively negative correlation. And if you write the equation using your calculator, you're going to find that it comes out to y equals negative 1.5x plus 9.8. Okay, so if you enter that data in, you should get that as your equation. If you're not, again, let's go back. You can look at how are you entering things correctly? Are you hitting the right buttons? Again, the sheet there shows you exactly what buttons to hit step by step. Take your time going through it. It might take a little while the first time, but once you get used to it, it's really going to be a lot nicer and easier than having to do this by hand. And then once we have that equation, again, one of the more important things we can do is we can take this and figure out what's going to happen to the output when the input's 12. So we could plug a 12 in there. What's going to happen when the input's negative 3? We plug a negative 3 in there. And we could do the calculation. So for instance, we could do y equals negative 1.5 times 12 plus 9.8. And we could see what's the output going to be when we put in negative 1.5 times 12 and then add 9.8. And if you do that, you're going to end up with negative 8.2. So you could say that you'd have a point then of 12 comma negative 8.2 that goes along with this data that would basically follow the same trend as the data that we see here. All right, so get comfortable with how to work with these, and especially if you get comfortable with how to do them on the calculator, we can do a lot more interesting things, and we can use these lines to make some predictions and work with some real-world examples. So keep practicing it. It'll come easier, and we can use that calculator as a great tool to help us with some of these things that can be a challenge and a little bit of hard work doing by hand.